everyone, we're back for day 2. Today I'll be going over a paper called Image Style Transfer Using Convolutional Neural Nets, written by Gattias et al. In 2016. And pretty much what the paper is about is you're able to take two different images and you take the content from one image and the style from the other image and merge them together to create a new image that has your desired style and your content. This is almost magical. Using traditional computation, there would have been virtually no way for us to write like if-else statements to be able to create this sort of output. And it just got me really excited. During the past couple hours today, I've read through the research paper, understood it, and actually recreated my own image style transfer algorithm, ran it on Google Cloud, put in my own images, generated some pics that look like these. So today I'll be sharing with you all the math and theory behind image style transfer, and then in tomorrow's video I'll show you what I built and how it works. Let's just hop right in. This paper pretty much does style transfer with the help of a convolutional neural net. CNNs are neural networks that are typically used for everything image related. How a convolutional neural net works is you have different layers, and in each of your layers a new feature is extracted. In between these layers there's a max pooling layer that discards spatial information. So what ends up happening is as you propagate down the layers, you end up at the end with an image that's very content focused and doesn't have a lot of the spatial information. That's why later layers are sometimes even referred to as content representations of an image, because it's just so much content. Style includes things like texture, color, curvature, and in order to detect the style, we're actually going to create a feature space and look for correlations between features in one convolutional layer. Each layer in our CNN has some sort of depth. It starts off more shallow, but as we progress down the CNN, the layers get more deep. And the depth of the layer corresponds with the number of feature maps in that layer. For each feature map, we can measure how the detected features correspond with each other. And the similarities and differences between each features, things like, are there any similar colors? Are there any similar curves? Are there any similar brush strokes? These things will give us more insight into the overall style of the image. How do we create our target image? Well, we have to make sure it has the desired style and the desired content. And the way to make sure it has the desired style and content is to try to minimize our loss function for content and minimize our loss function for style. For our content loss function, we take the mean squared difference between the features of our predicted image, so our created image, and the features of our actual content image. And we take that content image value from one layer. Typically, in this model, we would take it from con4_2, meaning we would take it from the fourth stack's second layer. So we take the content image from the fourth stack second layer, and then we compare that content image with the image that we've generated. And we try to minimize the differences between these two images. The way we minimize these two differences is once again by taking the gradient, and we edit our created image using backpropagation to find the gradient, edit the image, and optimize the image such that we get the least difference between the two. For style, we actually take correlations at multiple layers. This allows us to get a multi-scale representation of our style. The style values of an image as it goes through the CNN is calculated at each layer. And at each layer, it's outputted as something called a gram matrix. A gram matrix allows you to vectorize a 3D layer and make it 2D. And the gram matrix has information about the styles at each of the different layers. What we do is we actually calculate the inner product between the vectorized feature map at two different positions in one layer. Then what we do is we calculate the mean squared difference to be able to find the loss at each individual layer. Then from there, we would add up all of the individual error functions that happened at each individual layer. And we take all of those, make them into one overall style loss function. We would then take the derivatives of the loss functions, especially at the individual layers, the gradients can be calculated using backpropagation. And then from there, we would be able to minimize our error and get the output value that we want. Remember, we're not training anything. We're just changing our target image's style to try to minimize our error with backpropagation and optimization. In order to get a good final image, we need to actually minimize the loss function of both content and style. So it helps to merge the two loss functions into one overall loss function. Something really fascinating though is that they noticed that because we calculate style functions loss and content loss in two different ways, they're actually on two different scales. So what ends up happening is you can't simply add them. Instead, you have to add coefficients or weights in front of each of the two. In practice, the beta or the style weight needs to be multiplied much more in order to reach the same level as content loss. But something really fascinating that you can do at this point is you can actually tweak around the values of alpha and beta, these weights on each of these loss functions. And when you tweak around the values, let's say we increase our beta value, so we increase the importance of our style. If we do this, then our final image will actually have more style and less content. Whereas if we increase the alpha value, then we find that our final image has more content and less style. So you can play around with these values, and in the research paper they did, and they saw these really awesome combinations that occurred when you changed around the weights. These weights are good things to change if you want an exactly stylized or content-heavy version. That's great. So now we understand the theory behind it all, and then tomorrow I'll show you my recreation of their algorithm in order to create my own style loss transfer error algorithm thing. Yeah, woo! Have a nice day.